All right, everyone. How are we doing today? Doing all right? Okay. I think finally for my my setup here and the teaching station that things are going to be stable for a little while. At least that's what I was told when I spoke to one of my colleagues earlier, who is our departmental tech person, but not the person who is responsible for what's been going on in here. It's day 4, right? Okay. All right. Well, glad to hear that people are doing all right. Let's launch into this. I really should save this link. All right. Sorry, I'm getting logged into Bioshock here. I'll switch over once my session's open. All right. So logged into MATLAB now. Okay. There are a couple of things that I need to put up on Blackboard for you all to look at, but we're going to be continuing on with our exploration of the MATLAB interface. Okay. Last time we looked at this link here, which was the MATLAB integrated development environment, and kind of perused our way through the interface and talked about several different things, okay, including the interpreter and other things, a little bit about debugging and some of the built-in MATLAB libraries, and then finished off things by showing how to search the MathWorks website in order to find functions, including like the giant list of all functions, which is this thing here, which by itself is a little bit difficult to traverse, but it kind of gives you the idea that there's probably thousands of different function calls that can happen. So to be ready for all that. Okay. So next up, let's take a look at the next page here, which has to do with elements of MATLAB commands. Okay. Need to fix the numbering on the sections here. We'll get that taken care of. Okay. We sit here at kind of an interesting intersection between needing to use mathematical knowledge and then needing to adjust that mathematical knowledge to process it through the language of computers and to be able to communicate with them. So one of the things that we're going to be utilizing is our mathematical knowledge up through Calculus 2 and adding to that some bits and pieces of linear algebra. Okay. There are several things that as you take a couple more math courses beyond what the prerequisites set for this course are, you'll see is that there is a lot of pervasiveness of the discipline of linear algebra in the way that we frame certain types of problems. Okay, there are bits and pieces of linear algebra that will show up in Calculus 3. Okay, there are bits and pieces of linear algebra that will show up in differential equations as well. Okay, and each of those three things, linear algebra, Calculus 3, or vector calculus, and differential equations, all have a very intimate relationship with numerical computation. Okay? All three of those disciplines feature problems that are sophisticated enough that we often would like to employ a computer to help us do things like visualize the information. Okay, that's the number one thing that computers allow us to do in those fields, as well as to tackle problems whose analytic answers, which would be the ones where we would solve and write out the formula exactly, can be challenging to come up with, or even if we have those analytical formulas, they might be complicated enough that we need a computer to help us interpret what's going on. One possible example of this would be if in differential equations, we imagine that the solution of a differential equation looks like a Taylor series. Okay, so we have this infinite polynomial, and what we can do is we can determine enough information from the differential equation about the form of that infinite series. But unless that infinite series happens to follow one of maybe a dozen different patterns, and of course, a dozen is not very many when you're talking about the space of all possible things that might happen, you end up with a series that you can describe but doesn't line up with anything that we happen to know what it looks like. It doesn't look like sine, it doesn't look like cosine, it doesn't look like exponentials, it doesn't look like logarithms. And if it doesn't look like one of those things, we're pretty much sunk when it comes to being able to graph the thing. So what we do instead is we say, okay, computer, here is what the first 15 terms of this Taylor series look like. What I want you to do is plot a bunch of numbers and then add up these 15 different terms for this polynomial and then come up with a numerical approximation to what that solution looks like. Okay? Now, I said a bunch of words that you all should know at least more or less what they mean, right? Okay, especially the part about Taylor series and Calc 2. Okay, might have been a minute or it might not be quite so fresh because it's the beginning of the fall semester and it was wet this morning and 100 degrees outside, so it's pretty bad. I'm actually curious since I want to make a joke about it. We'll look it up. One of the ways, by the way, that you can tell how uncomfortable the weather is going to be outside is instead of looking at something like the humidity or the temperature, you can check the dew point. Okay. And what the dew point will do is basically allow you to interpret the relative humidity versus the temperature. Anything above 65 in the dew point feels pretty terrible. Anything above 70 is tropical and dangerous to your health for long periods of exposure. This afternoon at about 2 o'clock, the dew point was 71. I don't know if you had the unfortunate experience walking around outside, but it was not great. Right now it's 67 is what it says outside, which isn't much better. Anywho, but another thing that we could, of course, theoretically do is process large-scale temperature information from many different places in the country and be able to generate what that computation looks like and determine the dew points for a bunch of different cities, right? And so many things to do. Okay. Now, for our purposes, we need, as we go through the material here, to understand that there are going to be adjustments or special considerations that we're going to need to make for the material and the way that we think about problem solving specific to using a computer to solve a problem. Okay. There are things that we can do that computers can't. Okay. And there are ways that computers can solve problems that to us would be terribly inefficient, but it turns out the best way to utilize a computer to do this thing. All right. So we'll see some different examples of this, different algorithms and things like that. And then here there is a kind of facetious example of how one would think about computer programming. Okay. The main thing to remember about computers, especially if you are giving them a program to work with, is that they will only do exactly what you tell them to do. Okay? You have to be able to communicate with the computer in its language. All right? Now, this is a language that we're new to, a lot of us, okay? And is a way of thinking that we are also new to. So be a little bit patient, both with yourself and with the computer as you're adjusting to this process. All right. Okay. So let's start off with a relatively simple example. Okay. What we want to do is we want to find the roots of a quadratic polynomial. Okay. We have a method for doing this. What's that method called? I need to find the roots of a quadratic. What do I do? It's a quadratic formula, right? Okay. Someone was not quite singing the song, but explaining what the quadratic formula here is for those of you who are out there on the internet, which is correct. Okay. Now, it turns out that the quadratic formula works excellently, except it's actually got some problems if we ask a computer to perform that computation. Okay, so let us do an experiment here. Okay, so what I'm going to be writing here is our first MATLAB function. Okay, I'm going to call this quad form as a shorthand for quadratic formula. And just as a little bit more specific explanation of what's going on here, I right-clicked this. Sorry, I right-clicked in the current folder window here. I went to New, and then I selected a function. Okay, what that does is it creates a MATLAB file, and it immediately gives me an opportunity to rename that file, which I did. Okay, and since I did that, it went ahead and added the name in a couple of places here in the file. If you don't immediately rename it, it won't make that update, but it doesn't matter because you can just open the file and change the name to whatever it is you decide to name it. It's not a big deal. And then there is a little bit of preloaded text here. Okay, this preloaded text is sometimes called boilerplate. Okay, it basically is just a template for a starting function, and we can delete most of this, but it gives you kind of a starting point for how things are written down. Yes. Okay. You right click in the white space over here in new folder, and then you have many options. The option that I selected was function. All right, and then after you click that, of course, you can see that it'll say untitled, and then you can type in a name. Yep. Okay, so we have this. All right. Now this is supposed to tell you about where some things go for this. What we're going to do is we're going to change the names of the output arguments to x1 and x2. And for our input arguments, we want there to be 3 of them. And so we're going to replace where it says input arg1 and input arg2 with A, B, and C. Okay. What this is going to do is it's going to allow us to give the coefficients for our quadratic polynomial as inputs. Okay. The very first line here is a single line description of the function, okay? And then every subsequent line here that is showing up presently in green um, will be a detailed explanation of what the function does, okay? On the MathWorks website, we looked at a couple of functions and clicked on their pages and then saw the website and have everything explained, right? Okay, the documentation for the function. This is actually how in MATLAB the documentation for functions are stored, okay? So you can use the help command and then help and then the name of a function and it will give you information, okay? I can, for user-defined functions and also for the functions that are stored here in MATLAB, typing in what I'm about to type in is how you get the help command to give you information about the function. That's how it's stored, okay? And also, so you know, any line in MATLAB that has a percent sign in it, percent sign is the comment symbol. So any text following the percent sign is just read as text, okay? It isn't something that the interpreter looks at and tries to execute as code. It just is a way to leave notes. Sorry. Okay, so this now explains what the code does. All right, I haven't done any typing to actually change how the function works. And I'm going to delete these two lines just so that they don't give us trouble. And then we'll replace them with actual operative code here in a second. But I do want to show you that now, after I've made those changes, if I type help quad form, it gives me the information, okay? So one of the things that, as we move forward and write functions, that I'm going to ask you to do is put in this information for the functions that you write and submit to me, okay? One of the things that happens in programming is you will make a program that solves a problem, right? And you've written it and you know that it exists and you know that it works, okay? Or at least you hope that it works. Eventually you get it working. And at some point in the future, you have to come back to it and use it, okay? And one of the things that happens as you're writing programs is that you try to be clever, right? You try to keep the program short and you try to keep the program efficient. What's difficult to remember sometimes is what in the heck were you thinking, all right, as you've come up with whatever clever trick solves the problem. And if you have to make changes to it or add things to it or adapt it for some other purposes, if you don't have an explanation to remind you what the thought process was or what equation you're referencing or what the format of the data is that is input or output by the program, then you're sunk. Okay, so you want to leave this information for yourself so that you know what the purpose of the program is, and then if there are clever tricks that are employed or things that you looked up somewhere, that you look them up in this place so that you can find those resources again and refresh yourself in where the mathematical technique came from. Okay. There's a question in the chat asking if this is an exercise that you should be doing with me. It doesn't hurt to follow along if you can, but if you're in a situation where it's difficult to manage multiple screens, that's okay. I mostly want you to watch, and there's a relatively minor, there's an important result that I want to show you, but I want to introduce a lot of these things so that it's not the first time we've seen it when we get into the function writing process for ourselves for doing exercises and homeworks. Okay. All right. So let's open this back up. Okay. Now, we know that the quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay. And so what we want to do is write that out. Okay. One of the things to be mindful of here is you have to use parentheses for your grouping symbols. Okay. I don't have like a big horizontal bar that I can use to write large fractions. Okay. And so in order to make sure that that 2 times a is all in the denominator, it has to be in parentheses. Okay. Another thing that we can do, and the reason why this thing is angry and highlighted in yellow, is that it wants me to put a semicolon at the end of that line, because if I type a MATLAB command and I end the line with a semicolon, what will happen is it will not output the result to the console. It will do the computation, but it won't print the associated text. So it's the difference between doing this. Okay, it still does the computation, but it just doesn't put the output on the console. If I'm writing a function that does several calculations, I don't want to see all the intermediate steps. Okay, so generally what we do is we tell it to suppress the output of the intermediary computations and then only worry about the final result, the thing that gets returned by the function. Oops, sorry. Click the wrong thing. All right. Okay, so that should be the first root. And what we want to do is compute the second root here. Okay, so we type out the same formula, except now we have the minus sign. All right. Maybe we wonder, since we compute this quantity twice, if it wouldn't be more efficient just to compute that once and then recall the value. But that's something to think about here in a second. We'll play around with it. Okay. So we have this expression. And what we want to do is we want to find say the roots of this polynomial. Is that one that we know how to deal with? I hope so, right? We want to find the roots of this. Okay, we can factor, everything's fine. It is important when you're getting started to check your code against examples that you know what the answers are. and then to test it against the ones where you're maybe not so sure. Okay, so what we can do is we can say that x1, x2 is going to be equal to quad form, and then the way that we input a, b, and c is we just type the numbers separated by commas that are the coefficients for this polynomial. So it'll be 1, -2, 1. Okay, and it tells us that the roots are 1 and 1, like we would have expected, right? Okay, we can test other polynomials. One of the things that we can do would be to say, make up a problem where we know the answer, okay, and then work from there. And then see whether or not this works. Okay, and then that's the roots for the example that we just made up. Everything's fine. Okay, our program works. Don't we feel great? Okay, let's not get too excited. There's some other stuff to worry about. What about this? Can we factor this? It's not factorable, is it? Okay, that's all right. I mean, we're using the quadratic formula. We might as well use that, right? So we can say that x is equal to -b, which is 1, plus or minus b squared, which is 1, minus 4 times 1 times 1, all over 2 times 1. We get the square root of -3 over 2 for our radicand and the denominator there. And so we get -1/2 plus or minus the square root of 3/2 I. Right? That's a perfectly valid set of roots for a quadratic formula. But we, of course, have to now check to see whether or not this gives us a useful result. Okay. Looks like it might be right. And we can double check to make sure that the imaginary part is indeed the number that it's supposed to be. And to numerical computation, that looks okay. So even in the case where complex numbers shows up, the way that MATLAB has its built-in arithmetic functions saves us from this computation being an issue. Okay. Now, that kind of exhausts the set of normal cases, all right? For the most part, I would imagine that at this juncture, we would say the thing works. We've tested it in kind of the reasonable situations, right? It should work just fine for anything that has real roots. Okay, we've seen that it works for complex roots. And we know that complex roots always come in conjugate pairs, so that's going to be fine. All right. But there's a new type of question that we haven't asked yet. Okay. And this is where the trouble arises. Okay. Sorry, there's a question.
Could you show your platform again? I'm trying to do it on my end.
Okay. It's easy to have missed a parenthesis or something. All right. Okay, sorry. The thing that we haven't tested yet are the problems that are introduced by the fact that the arithmetic that's being done here is finite precision arithmetic. Okay? There's round-off error that is inherent to the way that computers do their mathematics. Okay? And if you are picking problems that are in that realm of the numbers that the computer has to distinguish between are too small, okay, then the computer can't properly distinguish between them when they're doing their arithmetic, and the round-off errors will kill the accuracy of the computations. Okay? So this is difficult to interpret unless we have the right kind of example. So let's take a look at this. Okay? So this is a very, very weird looking number. All right? We have x squared minus 10 to the 8th power plus 10 to the negative 8th power times x plus 1. Okay? Now, the question about this is, can we figure out what the roots are for this quadratic r? We got the quadratic formula, right? So let's start there. Oops. So it looks like this, okay? So I want to make sure I get this right. I'm not misremembering what that interior coefficient looks like, am I? Sorry. Huh? You mean a 2 here? You're asking if I should put a 2 here or something? Oh, I see. Never, all right, I got you. Thank you. Okay. So we add these two things together. We get this expression now. And then this thing can be rewritten as a perfect square, right? It can be 10 to the eighth minus 10 to the negative eighth, quantity squared, because it's basically the polar opposite of this, right? If you put a minus sign in front of the 2 there, it becomes, instead of 10 to the eighth plus 10 to the negative eighth quantity squared, you get the other sign. So this is 10 to the eighth minus 10 to the negative 8 quantity squared over 2. And so now so keep writing 18. Okay, the whole point of doing this is that now if we take the plus, those add out, right? If we take the minus, those add out. Okay? So what it gives us is the roots for this are 10 to the eighth power and 10 to the negative eighth power. Okay? Hold on. If I take plus, we get this. Yeah, they're positive. They're positive because it's a quadratic formula, not the factored form of the polynomial. But thank you for double checking me. There's a minus sign hidden at the very beginning of the problem that fixes that. That's what the minus sign's for. Okay. So I recognize it's a little bit convoluted to get to this point, but we have to have an example that demonstrates our dilemma. Okay. So what I want to do is I want to look at x1, x2, and then quad form. And then, so we have negative 1e8 plus 1e negative 8. This is a shorthand that you can use, by the way, to type numbers in scientific notation. The number before the e is the number that you would have in the first part of the scientific notation. E in this usage, if there's no spaces, means times 10 to the power So this says negative, whoops, that minus sign is supposed to be in front of the parentheses. This says 1 times 10 to the 8th power, and this is 1 times 10 to the negative 8th power. Okay. And we can put in our numbers here. Okay, we get our roots. And is there a problem? That's not the answer we were supposed to have gotten, is it? I got one of them, but I didn't get both. Okay. Analytically, having worked out the problem by hand, we see that like there's a symmetry in the way that the roots arise, right? Okay. And the trouble comes from the fact that this number put into the computer isn't one that it can store properly. Okay? Because in the digit that we can't see, there should be a 1, right? It should be 1 with 8 zeros, and then look like this, right? But the problem here is I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 digits. And all 17 digits matter. Okay? The computer stops at 16. All right? And so because the two relevant pieces of information are separated by more than 16 orders of magnitude, the computer can't numerically resolve the computation without some extra direction. Because what did I do wrong here? Oh, it's the same problem. Okay. Sorry. X2. Notice, it's exactly the same set of wrong numbers, right? Okay, so it has to do with something inherent in the way the computer is solving problems. That's an issue. What I tried to do was I tried to plug in 100 million, which is one of the roots, into the polynomial and evaluate that numerically to C0. But I still have this problem. Okay, it can't resolve that computation with that coefficient because it can't store all the necessary information in order to do that computation. If we work this problem out by hand and plug in that number, very obviously, okay, 10 to the 8th is one of the roots and 10 to the negative 8 is the other root. Okay, so this is a situation where you are better than the computer, all right? And we can ask questions, even though we have to contrive things a little bit, that the computer cannot answer. It is not capable of doing the arithmetic necessary to resolve this. And the reason has nothing to do with the algorithm. It has to do with the way that the computer stores its information. Okay, question over here. Okay. All right. I think I accidentally answered whatever the question was. Was it why doesn't it work? Yeah. Yeah. Okay. Yeah. So just for the benefit of the video, The student was asking basically if it was a storage problem. Okay, the number is too large relative to the way that the information is stored in the computer, and that's what caused the problem. Okay, so one of the things to be aware of that's connected to this idea is there is a concept in computer languages known as machine epsilon. Okay. Now, we know from calculus that epsilon tends to be a variable that shows up when we were typically referring to a very, very tiny number. And as we can see on the screen, that's the case here. Okay. Machine epsilon is the smallest number that a computer is capable of storing. Okay. Now, I want to be a little bit more specific in that statement. Okay. What machine epsilon really is the smallest value that a computer cannot distinguish between. Okay. So if I take 1 and add machine epsilon to it, I just get 1 back. Okay. Because the number that I'm adding to 1 is so small that the computer can't tell the difference. So to a computer, machine epsilon and, 1 and 1 plus machine epsilon are equal to one another. Because adding epsilon to 1 doesn't change the value that's stored in the computer's register. So that's actually the definition of machine epsilon, is the largest number for which this is true. Okay. And the number that's displayed on screen when I typed EPS, which is one of the built-in variables in MATLAB, is basically the smallest number that can be stored in the bit register. Okay, so there's a memory address that has a certain number of spots. Okay, the smallest floating point quantity that is addressable. Okay, and then this is the number associated with it. Now, obviously, there's some stuff that we can do with the exponent to like make the number bigger, make the number smaller. So, like, we can scale using scientific notation or multiplying by some power of 10 what's going on. But as far as comparing two numbers that are on the same order of magnitude or stored in the same way, this is the smallest difference that the computer can discern between two values. I feel like I'm over-explaining and it's causing problems. Okay. This is the main thing. If two numbers are machine epsilon apart, they're indistinguishable. Okay. The reason that this is an issue is that there's a 17 order of magnitude difference here between those numbers. And that's smaller than this. Which is why the computer can't tell the difference between this and this. Okay? Now, I should just get 10 to the minus 8. I shouldn't get all that extra garbage. Okay? All that extra garbage comes along from the fact that the computer does the numerical computation and then just hands me all of the leftover stuff that's saved in the bit register. Okay? These numbers just come from whatever happened to have been stored there from the last computation. Okay? This is another computer-only kind of problem. basically. All right. Now, these behaviors have been known for quite some time, and so there are steps in particular computer languages that are taken to mitigate these sorts of things. For instance, the example for this exercise that we're doing with the quadratic and solving here comes from a textbook. And 2 versions of MATLAB ago, you could do 10 to the 7 and 10 to the minus 7 and have it work. But they made MATLAB better at doing arithmetic. So that example doesn't work anymore, so I have to do 10 to the 8 and 10 to the minus 8, which is pretty funny to me. So if I make this difference smaller, oh wait, it doesn't work now? Okay, all right. That number is very, very close to 10 to the minus 7, but it's not exactly 10 to the minus 7, which is unacceptable, right? Okay. Another, we only have finite precision for our arithmetic, so we have to decide a lot of times when close is close enough. Okay. All right. Now, if we continue to reduce the exponents here, it gets better, right? But they're still garbage. Okay. So, you're smarter than the computer. All right, believe it. Okay. So, that was a pretty heavy digression, but what I want to do is show you what I would like you to do between now and next class. Okay. Have to get used to the meeting twice a week schedule. Okay. I'll post listings for these in Blackboard so you can take a look at them. Okay. There's another set of short exercises to do. I'd like you to do these before Friday. Okay. This is just a matter of typing in some basic MATLAB commands. It shouldn't take a terribly long time to work these out. Okay, some of the examples are shown, and then we'll talk a little bit about array slicing before we leave so that that's clear. Okay, and then there's some other stuff to do. You can follow along with that. And then there's also a set of homework assignments that are related, but will take a little bit longer to get all typed in. Okay, and I'll give you the weekend to do the homework 2 set. All right. Okay. So yes, the exercises. The question was which one is due before the weekend. When we get into a more consistent cadence for the class, I see that everyone here at least has laptops or is able, maybe gotten these things to work. Huh? Yeah. Yeah. So what I'll try to be more disciplined about in the future is having the exercises listed in Blackboard prior to class starting, and then the exercises will become in-class activities where you run through and we spend 5 or 10 minutes doing them just to make sure that everyone's following along and got everything going. We've still just kind of been talking through and me showing off stuff, so I didn't want to transition to that quite right away. And then of course there was the weird tech things that were being annoying. But that'll be what the exercises are for, and then the homework assignments will be the outside of class take longer sort of deals. Okay. And so probably the way that the exercises will work is I'll make them do like maybe the next day after class. So that way, if you don't quite get it finished, you don't have to just go home right away and do it. All right. You can pick it up sometime the next day when it's convenient, but they'll still be relatively short. Should be like a 10 or 15 minute sort of deal. Okay, so last thing for today, we're going to be talking about slicing arrays. If we have um, okay, an array that looks like this. All right, I just wanted to make up something that wouldn't take up a bunch of screen space, but would be interesting enough for us to take a look at. Okay, there are several different aspects to the way that this thing is indexed in MATLAB. Okay, the first and sort of most obvious is the row and column index, where you say A and then in parentheses report the order, or sorry, the row and the column that you would like to find. And what MATLAB does is it returns the element that is in the second row and first column. So I've highlighted here the second row, and then it selects the first column's entry and then returns that value. We can select different rows and columns, get a different value. This would be the fourth row, third column, and so we get this 5. Yes. Yes. So the question is about the function that I use to generate the matrix. The inputs for the function, and it will tell you this in the tooltip if you type rand I, is it creates random integers. I told it that I wanted it to make random integers in the interval from 0 to 10. Okay, and then I wanted to make a 5 row 4 column matrix, which is what those inputs are. Okay. When okay, all right. The other half of the question that's being asked is a student typed in the same command that I did and got exactly the same matrix as me. Okay. The reason for this is that randomness in computers is not random. All right. Whenever you have something that is supposedly generating a random number in a computer, it is actually using something called a pseudo random number generator. Okay. And every computer programming environment, Python, MATLAB, C, what have you, okay, has an algorithm that it uses to generate the random numbers. Okay, it uses the same algorithm and the same seed, which is starting point for that algorithm, so that the programming system has consistent behavior. Up until now, you and I have been using the same MATLAB because you probably logged into BioShock, right? Okay, so it's the same version, and you haven't done anything involving random numbers, and I haven't done anything involving random numbers. So we're at the first spot in the seed for the random number generator. So calling this command as the first random command that you do in MATLAB when you open MATLAB after having closed it will always give you exactly this matrix. Okay? Because they want the behavior to be consistent. If you want to randomize the seed, there are commands that say start at a different point in the sequence and then do the computations that way. Now, just as a test, if you do the same command again, you should also get exactly the same answer as me. Okay, so test that out. Just use, like, double click it in the command history or something. Okay, or you can just press up a few times to find the old command. Okay, someone else did it and they got the same answer. Okay, so that's what's happening there. Now, there's a funny story about in the olden days, you all are familiar with something called the lottery, right? Okay. Both of the national lotteries also, by the way, have relatively big jackpots at the moment. I don't know if anyone else noticed that. There's a big sign on my way home. Like one of them's at almost 300 million, and the other one's over 300 million. Anyway, um, it used to be the case that instead of making the show of having the ball pit with the air machine that like tumbles the balls around that they pick out for the lottery, that they would just use a computer and generate the lottery numbers by a computer using one of these pseudo random number algorithms. Okay. Um, that was fine, except someone figured out what computer system that they were using to do this with, like the actual computer chip that the lottery had set up. And because they could read what the lottery numbers were, could figure out where they were in the sequence for the pseudo random number generator. So they won the lottery 4 times in a row. Not in a row, they actually spaced it out, but often enough that they figured out that this person had to have determined the stuff. So that's why they actually do the process instead of using a computer to solve the problem, because it was exploitable. Okay. So anyway, there are things to do with this programming and math stuff. All right. You can strike it rich. Okay. And there's a question in the chat, a couple of them. Let me address these before we move on. Someone here in the chat asked if accounting for indices in MATLAB start at 1. Okay, and that is correct. And depending on what programming environment you're using, sometimes the first element of an array will be indexed with a 0, and sometimes it'll be indexed with a 1. In MATLAB, it's indexed with a 1. Okay. And then another question is about the rand_i command. It's asking what this first argument does. The first argument here tells MATLAB what the range of integers are that I want to be in my random set. Okay. I specified a particular range in this case. I could have just also set a maximum integer to do. And that will give me integers, I believe, from 1 to 12. I don't think I can get 0 if I just type in one number like this. And the different options. It's not showing me the tooltip. Okay. It'll give you the different options here, and then if you really want to see all the possibilities, you can always go to the website and look up this command, and it'll show more examples than what it'll display on the screen here. Okay. So let's use this matrix for A now. Okay. There's a second half to the question for rand_i and how the range of integers that I gave work. For other types of random commands in MATLAB, say the one that generates numbers from 0 to 1, or the ones that generates numbers on a normal distribution, okay? The rand_i command is the only one that allows you to explicitly, as an argument for the function, set the range of possibilities for the outputs. For the other ones, you generate the numbers and then want to scale them outside of the function. So for instance, if I wanted random numbers between 0 and 5, I would do 5 times rand and then whatever the matrix is, right? And that would give me a matrix of numbers between 0 and 5. If I wanted to go from -3 to 3, what I would do is take 6 times rand of a matrix and then subtract 3 to adjust it over, right? So it would go from 0 to 6, and then I would move it to the left by 3 and go from -3 to 3. Okay, so we can do rows and columns. Second row, third column. I can say that I want the second and third row and the third column, and get a chunk of the matrix, or a slice is the term used for this. Okay, so it gives me a 2x1 matrix that is made up of the entries in the second and third rows and third column of my original matrix. I can grab the entries in the second and third row and first and third columns. So second row, third row in the first column, second row, third row in the third column. All right, you get that little mini matrix. I can do this out of order. I can tell that I want the third column and then the first column, and you see that it gives me the answer that I had before, except the columns are switched. If I want, I can tell it to give me the same column multiple times. Okay, I can do this with rows too. I just don't want to make the example super complicated. All right, so we can do various combinations that look like this. Okay, I can, if I have some reason to, there's 5 of these. Reorder the rows or columns of the matrix. Okay, if I need to have multiple copies, I just type the same number multiple times. I can put it in whatever order I want. Okay, so basically each one of these that shows up here says make a copy of the whatever row of A, and then we can put it together. Okay, over here I used a colon. Okay, this colon is a way to say give me all the columns or give me all the rows. Okay, so I didn't want to leave out anything from the columns, and I didn't want to jostle the columns around or do anything silly with those. Okay, so I just say give me all the columns. So if I were to have just typed A2 colon, that says give me the entire second row of the matrix A. Okay, obviously we can do this with columns as well by saying give me the whole third column. Okay, and then I can say give me the whole first and third columns, stuff like that. Questions about this? Seems okay? All right. Now, there's one more thing I want to show you, but I want to check in with the chat before we do that. Okay. Don't see any questions there. If you do have questions before we finish up class, please type those in the chat so we can get those answered. Whoops. Yeah, I know. I don't have anything that's lowercase a. Okay. All right. Now, I don't know if I've typed this before, but I'll type it now so that we can see it. This is the empty matrix. Okay. Set of brackets with nothing but just blank space is the empty matrix. Okay. MATLAB considers this to be a 0 by 0 matrix. This is the way that we represent it. One of the things that we can do with a 0 by 0 matrix is if I take a subset of a matrix and set it equal to the empty matrix, it is deleted. Okay? Yeah, that the erstwhile second row is no more. Okay? So you'll see now that A is a 4 by 4 now. It was a 5 by 4. Second row is gone. It's gone forever. Those values cannot be recovered. Okay? They're no longer with us. Okay? And you can do this operation to delete rows or columns of matrices as you see fit. Okay? You can also delete like larger sections of the matrix. Okay, if I need to delete half the matrix, I can do that. All right? The rule for this is that I can't delete something that would result in the matrix not being rectangular anymore. Okay? Matrices have to be rectangles. If I try to do something to a matrix that makes it not rectangular, MATLAB will tell me no. Okay, I'll get an error. So I have A here. I can't decide that A22 here is going to go away because I would have a hole in the matrix. It wouldn't be a rectangle anymore. That's not okay. All right. So I will make sure that a link to the exercise is posted for this and the homework so that you can take a look at those tomorrow or Friday. And then I'll make the second homework assignment due on Monday so that if you have questions about those, we can talk about those after the weekend. And then there's a question. Okay. There's a question asking if instead of trying to delete the entry, if I want to change it to some value. Okay. And then the answer is yes, you can do directed assignment by this technique. Okay. Now, any of the slicing that we have been doing to refer to particular parts of the matrix, say here, we'll type A, and it looks like this. And then I can say that I want to change the second row of the matrix to some other set of values. Okay, I can do a directed assignment like that as well. So I can replace entire submatrices at one time by doing these types of computations as well. That's the next step, the application of having access to these indexing abilities. So thank you for the question. All right. Not seeing any questions in the chat. So if you do have questions, please send me an email and I'll get those taken care of. And for now, I wish you all a wonderful evening and I will see you next time.